So, hello everyone, thanks so much for coming. Also, good job, you've made it to the final talk of the conference. I'm Sergei, this is Mark. We both work as part of Google Project Zero. We both have been mainly focusing on Chrome research for the past few years. Today we're going to talk about escaping the sandbox in Chromium-based browsers, and more specifically, general approaches an attacker might take to exploit vulnerabilities in privileged browser components from a compromised renderer. So first, I'll give you a few examples of real-world sandbox escapes and describe one of our own latest full chains. And in the second, more technical part, Mark is going to present a new approach to exploiting vulnerabilities in privileged processes. So how do people escape the sandbox in Chrome? For many years, most real-world actors didn't even bother with attacking privileged Chrome processes. They would just go straight from the renderer to the OS kernel or a privileged system service, especially since their implants would usually require system privileges to work anyway. So such sandbox escapes are nice, they're reusable between browsers, for example. They live longer, we've seen them in the wild, and they are out of scope of this talk because they're not Chrome specific. Luckily, it looks like attacking the OS directly from the renderer is no longer in the path of least resistance, at least on some platforms. So maybe instead of working on the super duper secure mode, someone should work on stronger sandboxing primitives. But yeah, on some platforms, it is now easier to build a chain where you compromise the browser or GPU or a network process as an intermediate step towards getting superpowers on the target device. And how do you do that? Well, occasionally, security researchers find bugs in privileged processes that can be triggered directly from JavaScript or over the network. And you can actually check out our blog about exploiting such a bug in the Project Zero blog. But most of the time, you're required to have a more precise control over what's sent to the privileged process to trigger the vulnerability, which means you have to compromise the renderer first. And let's look at a few ways attackers abuse the compromised renderer. This first example is from an exploit competition. Most of the exploit is written in JavaScript, but the JavaScript code has to live patch a number of native functions in the Chrome binary. So exploits usually do that for one of two reasons: to remove some render side checks in order to trigger the bug, or prevent the renderer from crashing in the process of exploitation. And the second possible reason is that you might need to modify some data that will be passed through an IPC channel in a way that's just impossible during the normal browser operation, like corrupt some length field where the length calculation is always correct in the renderer. And the main disadvantage of this approach is that the necessary modifications are unique to each bug, so it takes manual work to implement them, and quite possibly it takes extra work each time the browser is updated. There also might be subtle side effects which will reduce the stability of the chain, and most productionized exploits actually don't work this way. The exploit we discovered in the wild in late 2020 takes a different and more conventional approach. In general, in the wild, browser exploit chains consist of isolated, interchangeable components, since it makes maintaining the capability easier. In addition, it allows the attacker to do a bit of extra profiling from the renderer process and pick the most appropriate sandbox escape. So the renderer exploit usually doesn't provide an interface to a later stage. It doesn't expose an arbitrary read-write primitive or a function call primitive. It just receives a binary blob with shellcode and jumps at the beginning of it. This exploit is a small handwritten binary that supports 4 major versions of Chrome. The developer had to maintain a list of version-dependent constants and a few bits of version-dependent code. So the exploit looks up a table of IPC functions known as the Mojo system API, and more on that later, And interacts with other processes at this level, which is roughly in the middle of the Chrome IPC model. The actor has definitely spent a lot of time on the Sandbox escape exploitation framework, but there's still a fair amount of manual labor required for each new bug and exploit. Also, the exploit has to do things like going through 9 levels of indirection just to get an IPC handle, but that is just an unavoidable consequence of Chrome's code complexity. And the final example is also served to a target as a binary blob, but this one is much bigger. There's a small bridge layer that looks up a few pointers in the process memory and initializes a few structures. There is the core exploit logic, like the main function, but virtually everything else is just a copy of Chrome that's compiled into the exploit, to the binary blob. And it's the first time in my experience that recurrent symbols in an exploit with bindiff was effective, as you can see on the screenshot. These nice C++ function names. There's likely a separate build of this exploit for every separated version. And interestingly, it seems like the most advanced framework with little to no manual work required per browser update. But, well, I hope you agree that 2 megabyte shellcode is not the most elegant thing you've ever seen. These 3 examples more or less represent all the Sandbox escapes, or rather the Sandbox escape exploitation approaches we've seen in external exploits. Well, we don't like them. We want our exploits to be in pure JavaScript. So, story time. Why is this picture on the slide? Should one of the keynote speakers be concerned? Not really. There is tradition in the security and privacy teams at Google. If you're leaving the team or leaving the company or moving to another office, like another country, you can challenge your colleagues to own you and steal your password. Your goal is then to defend yourself. This counts as a security exercise, and it leads to interesting discoveries. It allows the defensive teams to improve their detection, for example. Most importantly, just a fun way to, a way to have fun at work and actually use some of your 0 days. Time is usually a constraint in these exercises because not everyone announces their departure too well in advance, and the fact that the target expects you to tag them in the next few weeks makes it even more exciting. So a little more than a year ago, we learned that Justin Shu opted into the tradition. You might know him as one of the authors of this book entitled The Art of Software Security Assessment, but Justin also spent more than a decade securing Chrome, so it naturally made sense to own him with the Chrome full chain. We knew that, as most Googlers, Justin primarily used his Chrome OS laptop. We suspected it might create additional challenges, and it did. So just a couple of words about the renderer bug. We tried to cut corners, obviously, and build an end-day chain first. So started by looking for recently fixed issues that hadn't yet made it into the latest stable release of Chrome. And Chrome OS actually helped us because it lags a few days behind other platforms. So, and as a lot of you probably know, the best place for finding fresh renderer bugs in Chrome that are easy to exploit is v8/source/compiler, the Trugafan. This change immediately caught our attention. The bug, it fixes, makes the compiled code produce an incorrect result for an arithmetic operation. And you can use it to create a type mismatch and then exploit it like a classic typer bug. So the cheat compiler bugs are so powerful, and they have been so thoroughly studied, as Amy and Samuel's presentation should have convinced you, that it literally takes minutes or a few hours in a really bad case to repurpose your existing exploit for a new bug. That's exactly what we did. So with the renderer quickly out of the way, we moved on to the Sandbox escape. Unfortunately, we couldn't find any NDAs that affected Chrome OS and were easy enough to exploit, so we had to look for our own vulnerability. Our choice of the area to focus on was inspired by an in the wild bug we investigated just a few weeks before. And that area is the layer that translates IPC types in Chrome into native C++ types. This is done automatically most of the time, but in some corner cases, the developer has to implement the serialization and deserialization manually. So in our experience, performing variant analysis on an in the wild issue almost always leads to the discovery of at least one related issue or a variant. This is not the case for any other type of external or internal bug report. Almost like people selling capabilities don't like bug collisions and choose to look for bugs in more obscure areas. So on this slide, you can see the definition of a Chrome IPC data type called data element, written in Mojo IDL. Data element is essentially a union type, but it was defined as a regular structure, emulating a union with a few shared fields. On the right, you can see it redefined properly after the fix. The problem here is that several data element subtypes need to track the length of the element, but one of the subtypes, namely kbytes, already stores the length internally, and the deserialization code doesn't check that the two values match. This is the deserialization function. Out points to an object of the native C++ data element type. Out buff is a nested vector that's initialized with the data we control, and out length is initialized with an independent value, essentially, which we also control. Of course, the code that deals with serialized data elements, with deserialized data elements, fully trusts the length field. We unfortunately can't sit on 0 days at Project Zero, so we had to report the issue to Chrome before continuing. But the bug seems pretty powerful, and it's a classic primitive. We have a buffer in which we control the fake length, the actual length, and the contents. Unlike the original in the wild issue, though, a privileged process will never write anything to the buffer. The only thing it can do is to send the contents of the data element to a remote server as a body of an HTTP request. Luckily for us, our colleague Stefan has discovered a technique for exploiting info leaks in privileged processes. Actually presented it at this stage in the last OffensiveCon. It turns out that in Chrome, you can talk to an IPC interface as long as you know it's a 128-bit secret port name. Well, to be honest, you can no longer do that. Stefan has finally killed the technique in Chrome 99, so in a few weeks it will become useless. The vulnerable code, though, handles HTTP requests, so we must be in the network process. This event has some advantages, because if our sloppy exploit crashes the process, it will get restarted automatically without notifying the user. But there are not too many privileged interfaces in that process, and most of them are created early in the process startup. So we couldn't groom the heap well enough to just steal the interface name of our choice with a single info leak. The best strategy we came up with was to spray the heap with the target port name by repeatedly calling a method on the target interface. And we can do that directly, obviously, but we can ask the browser process, or we usually can find a method that will trigger some method in the network process through the browser process. And from another thread, at the same time, would trigger the bug, basically collect everything that looked like it could be port name and check if it's the port we need. The process would take some time, and it was also dependent on the internet bandwidth because we actually had to send the leaked data over the network. Yeah, and Justin could just close the tab before it finished. Also, heap spraying a lot of stuff from multiple processes or multiple threads is CPU intensive. So if we didn't succeed quickly enough, the fans on the target device would start spinning 100%, which was slightly suspicious for our target. We didn't have enough time to find a better bug, so we just came up with a workaround. Decided to hide the process after we successfully exploit the initial issue, the V8 bug, then wait and continue at a later pace, hopefully without triggering too much attention. Yeah, by default, the renderer is terminated shortly after the page is closed. We can avoid that thanks to shared workers. The shared worker interface represents a specific kind of worker that can be accessed from multiple windows at the same time. And as you can see from its Mojo interface, the shared worker and the process it lives in will be terminated after the last connection to it goes away. From a compromised renderer, if we have an arbitrary read-write, we can just essentially connect the worker to itself, creating infinite loop and preventing the process from being terminated until the whole browser is restarted. The trick worked pretty well. The laptop would no longer turn into a jet plane. We just needed to find an IPC interface to attack. This is a network service, the main Mojo interface of the network process, used solely by the browser process, and it has one curious method that allows you to set up the full path to external GSS API library that gets loaded when Chrome receives a 4.1 response from a web server. That's right, method just loads an SO of your choice. Very convenient. All that's left is to drop a file on the target's disk. Yeah, there's a lot of different ways you could use to drop a file. You could abuse HTTP cache, force a download, but there's an even better way, because the IPC interface that acts as the backend for the HTML file system API has the method getPlatformPath that just returns you the full path to your web file system file. It's obviously not exposed to JavaScript, but nothing prevents a compromised renderer from calling it. We put all the parts together, popped calc, and we'll learn the hard way that Chrome OS isn't Linux, because in Chrome OS, the user data folder, which is the only folder we could drop files in, was in non-executable mode. We were really running out of time at that point because the new Chrome version came out with both of our bugs fixed. Justin essentially just needed to reboot his laptop. Since our goal was just to steal the password, we will settle on using another privileged method in the same network service interface to temporarily redirect all traffic to our proxy server and make the browser trust our certificates. Then we backdoor the login page by requesting it from the exploit, responding from our proxy, adding a couple of very aggressive HTTP cache headers and a bit of our own JavaScript. This is the final exploit flow. We have successfully stolen the password twice, actually, because Justin couldn't properly clear the cache for some reason the first time. The exploit has, well, a nice property. It's data only. Both of its versions didn't have to run any shellcode, didn't have to call any native functions, all thanks to Mojo JS. And Mojo JS is a feature of Chrome that exposes part of IPC to JavaScript. It's used by internal Chrome pages, but in a compromised renderer, it can be enabled by just overriding a flag. So why we're talking, the browser people in the audience might ask, why we're telling them about a technique that has been public since 2019. So because we want to show how fun exploitation is once you can do it from JavaScript. But this is an ideal case. We just got lucky with our Sandbox escape. That is, the interface the bug was in, and all the interfaces we used for exploitation were supported by Mojo JS. And in 2022, it's not the case for most of bugs and privileged processes reported to Chrome. Mark will talk about why it's not always the case and what to do about it.
Okay. Yes, it works. Good. Yeah, I hope everybody had a coffee during the break, because it's going to get much heavier from here on. And I don't have enough time to really do a full intro to Mojo. I did try to make those slides, but it was just too much. So the rest of this talk is basically we're going to follow a little journey into Mojo and JavaScript and how the two mix together. And it's kind of following a process that I went through after we finished analyzing the second Sandbox escape that Sergei mentioned before from in the wild stuff, where I said, oh, I don't understand Chrome Android Sandbox exploitation anymore. I need to go write an exploit for this bug just to, like, get that familiarity back. And then I got talked into, oh, well, you should write the exploit in JavaScript, and oh, actually, you should make the whole thing data only, and like, just snowballed from there. So yeah, quickly take a look at some Mojo IDL. So this is basically how your Chrome developer describes the interface that their service exposes. We've got a super simple example at the top. It's a small interface. It has one function. It takes a string argument. It returns an array of integers, right? In practice, the Mojo IDL lets you specify like arrays of maps of integers or arrays of maps of interfaces or all sorts of crazy things. But we're not going to go into that really today. The bottom two examples are a little more interesting. So those would be interfaces which, where they actually return a handle to another service. And there's an important difference between the two, which is the top one that returns a remote, and a remote is like a service binding which has its own message pipe. And an associated remote, that is like a handle to a service where you're actually sharing a message pipe between the parent interface and the child interface. And we'll see some examples of that in a little bit. But first, I've got a kind of, the writing's kind of small. Anyway, 10-mile view of the Mojo implementation in Chrome. So starting at the top, we have this client language layer. And actually, you can implement Mojo code in JavaScript, in C++, in Java, and in theory, whatever other language you would implement this top section in. And actually, the top layer in this orange section is automatically generated from that IDL code we looked at a minute ago. Underneath that, we have a C API layer called the Mojo System API, and that's where one of those exploits we saw was actually hooking into to manually do their Mojo exploit. And underneath that, we have a load of C++ code which actually implements all of this, and the platform-dependent stuff to actually send these messages between processes, which is obviously different on each platform. So, Sergei said a minute ago, like, yeah, this Mojo JS thing, it was talked about in 2019. I think I was maybe the first person publicly to talk about doing this. I don't know if anyone was doing it before, hands up. Yeah, so you have a renderer bug. There's a flag you can flip. You can reload the frame. You get these JavaScript bindings. You can talk Mojo. It's really sweet. Your exploits can be data only, right? So what does this JavaScript look like? This is just a small snippet of code to interact with the blob registry. Anyone here who has written a Mojo exploit probably used something like this, because it's super convenient for heap manipulation in the browser process. But yeah, the top 3 lines, we're creating basically a handle to a blob registry. We're binding that to a message pipe, and then we're sending that message pipe to the browser process and asking the browser process to actually connect that to the blob registry. The middle bit, this is just setting up arguments, whatever, some data, right? And then we have effectively a second IPC call at the bottom, where we're actually sending a request to this blob registry handle we created a minute ago. So far, so good. And for the 2019 exploit, and for the one that Sergei just discussed, like, this is enough. We can do everything we need. But he also said, yeah, there are some reasons why you can't use this. And shortly after that blog post, we saw like a lot of reuse of this technique in exploit competitions, in VRP reports, and it's kind of dropped off. Like, a lot of the bug reports now, and as you saw all the in the wild stuff, there's either renderer patches or there's like loading an ELF file or whatever, right? And there's a reason for that, and it's kind of illustrated here. So on the left, we have like 6 interfaces. These are possibly not all, but nearly all of the ways that the renderer requests a service binding from the browser process. And the bottom 2, which are colored in orange, they're actually exposed to Mojo JS. And the top 4, they're all channeled through this one big message pipe, this associated message pipe. And this isn't exposed to Mojo JS. There's a reason for that, which is that at this top level in the implementation we saw before, like the orange layer, you can't really share a single message pipe between multiple languages, because how would you know which of those languages was supposed to be reading the next message you got on that message pipe, right? It's just the way it's architected, it's not something that conceptually really works. In addition, it's actually not something that Chrome needs for what they use Mojo JS for, so there's really no reason that they would go and support it. So we need to find a way around this first, because the bug I was looking to exploit is in a frame-associated interface, which is up there in that top blue section. So we can't share a message pipe between JavaScript and C++, but we can man in the middle a message pipe between JavaScript and C++ and just proxy all of those messages through JavaScript. And you think, like, this is a lot of messages. This is like all of your frame manipulation, all of your DOM, like everything goes through this message pipe, but actually it works pretty fine. It's even better if you do it in a cross-process iframe and not the top-level window, because then you don't have any UI problems at all. So at this point, you say, okay, we're done. We have Mojo JS support for all of the interfaces. We can go and write our exploit. But one of the things that I've been talking to Chrome about, one of the things that came out of that 2019 work, was people saying, okay, we should just get rid of Mojo JS. Like, we should just not have this in any of these renderers that don't need it. And I said, well, it's not like, I mean, you could do that, but it won't prevent people from doing this. I said, like, you can just re-implement Mojo in JavaScript. Like, it's not such a big problem. And then we wondered, like, can you? Like, can you do that? We know JavaScript engines are super powerful, right? We know you have so much control, but can you really just re-implement Mojo in JavaScript fully data only and just not need Mojo JS at all? I didn't start with that, right? I'm not going to do some huge engineering project, just straight jump in. So I said, okay, what's the simplest way that I could go about doing this? So quickly, we'll just talk back about renderer exploitation. So I think everybody who's written a browser exploit or a renderer exploit will be like, yeah, these are pretty reasonable primitives to get from a JavaScript engine bug, right? Not your first order primitives, but your second order primitives, right? So you've got two type confusion primitives. You've got an arbitrary read and arbitrary write. Now, this V8 heap sandbox thing, right? Maybe this arbitrary read, arbitrary write is going to become hard. Who knows? Certainly the bottom two, we would hope that with maybe in 5 years' time, 10 years' time, we have super robust CFI, we have ACG everywhere, and these primitives are looking kind of questionable, maybe. I don't know. I would like to see that future, right? Is it going to make a difference for our sandbox escapes? So, yeah. So where do we start? Well, this is where Mojo JS actually sits in this implementation diagram, right? And it's very, very close conceptually to the blue layer underneath. So this is going to be the easiest way to sort of bodge ourselves together a new Mojo JS. And it turns out it's pretty easy. So using your function call primitive, you can pretty much just write some JavaScript that mimics Mojo JS, and 90% of this whole thing just drops out pretty easily. However, there is another 10%, right? And I guess I need to explain briefly what a trap is. So we've been talking about message pipes and sending messages between processes, but Mojo doesn't just poll message pipes to see when there is a message ready, right? You need something like select or some concept like this, because you have hundreds of message pipes per process. So trap is like the Mojo native equivalent of select. And what a trap is, basically you register a handler, you attach it to a message pipe, and when that pipe becomes readable, that trap will fire and your handler will get called. The problem for us here is this handler is a function pointer. And you can't really just have a function pointer to a JavaScript function. And I'll admit that I did actually spend maybe a day trying to think of how I could arrange things in such a way that I could have a function pointer to a JavaScript function. And then I was like, this is really stupid. I need to move on, and I will just throw some shellcode in here. So this is the first implementation, right? We have a handle to a message pipe. We have a watcher. It's going to watch that handle. We're going to add a trap in, and we'll point that call back to some shellcode. And what will that shellcode do? Well, we want this to be fairly simple, right? So we'll just have a big byte array over in our JavaScript, maybe an old space, something like that. And when that trap fires, the shellcode will just set the signal in this table, and we can poll it from JavaScript, and we can deliver our callbacks. Yeah. So where are we at? So at this point, we're feeling pretty good, because we have a complete polyfill for Mojo JS, and we're like, well, if they remove Mojo JS, who cares? I still have my exploit written in JavaScript. It's not a problem. But it's not really future-proof in terms of mitigations, right? And certainly not CFI compatible. I mean, I guess you all can probably produce those primitives right now, so I guess you don't care that much. But maybe in 10 years, I would like to think that those primitives are going to become more hard. And this idea of having shellcode in there, right, maybe with ACG and jitless mode, this is already kind of... So it's the first thing we want to do. We want to get rid of the shellcode. Yeah, I had to think, this was like my biggest worry in this whole project, right? How am I going to get rid of this shellcode? And I looked at a lot of the web platform, looking for places that Mojo is used and might be useful. And I found message channel. And so message channel is like a normal JavaScript feature. If you're familiar with post message channel is basically a way that some JavaScript code can create a new channel, and it can send part of that over post message so that you have a separate communication channel between two origins or two contexts, maybe a worker and a main page or an iframe. And under the hood, that channel is just a Mojo message pipe. So we replace our trap with a message channel pair. And if you can see, like, it's kind of awkward to point over there, but like this pair of message ports, they're effectively connected through some native code to a pair of message pipes which meet in the middle. And obviously, if this message port is going to work, it needs to get notifications when those message pipes are readable, right? And that's exactly what they have, right? So for each of these message pipes, there is a trap which is waiting on that handle. So can we just move that handle to point to our other message pipe and get notifications when that message pipe is ready for reading? Yeah, we can. I mean, modulo some gymnastics, but yes, we can, and it works. One of the problems here is that this message port interface, right? It doesn't send raw Mojo messages, right? Like, we can't just send whatever we want over that. It has some structure it expects. So we have to actually make sure that when our top message pipe, the one that we're actually interested in kind of polling, becomes ready for reading, well, this other message pipe has to have a message that's ready to be read, otherwise everything's going to get really confused. So yeah, we have to do a bit of gymnastics, but it's not actually as hard as it looked. So at this point, I'm like, okay, this is going to work. I think this is probably when I submitted the CFP. And I'm like, this is going to be, and then fast forward, you know, whatever. It's getting close to the conference. It's not actually finished. Because it turns out, actually, re-implementing message pipe is not as easy as you might think. There's a lot of code there. And if we go back to our little system diagram, it's actually kind of difficult to interact with the Mojo implementation at any layer other than the very bottom layer from like JavaScript in this data-only way. And the reason for that is just that almost all of these layers, they're kind of a pass-through. Like, they just call directly into the layer below. So if you're accessing this in parallel, like obviously the JavaScript thread doesn't normally send Mojo messages like directly. So the IO thread is constantly interacting with Mojo channels. We need some actual concurrency primitives. And the only place there's any locking or queuing or anything useful like this is right down in the bottom. So we're going to end up writing a lot of C++ in JavaScript. But before we do that, we'll take a look at what things look like at this very bottom layer. So this is basically, if we look at that JavaScript we wrote earlier, this is the first message which actually gets sent over the pipe between the two processes. I'm not going to go into it in detail, but the top green section is a load of different headers. The big red section is the metadata associated with the message pipe that's actually being sent. And all of the orange is actually generated from the IDL code. So that's not something that we have to build ourselves in this case. And again, we go back to like fast forwarding. I'm not going to show you all of this JavaScript code. I will hopefully release it at some point when I've removed all the to-dos. I'm not quite there yet. But this is std unordered map find in JavaScript. And compatible with libc++. And in order to get this message pipe stuff working, right, we're going to re-implement like half of base and half of libc++, just so that we can interact with the data structures safely or correctly. So the process I took when I was doing this, I would say, was basically like, I'm going to go rewrite a load of C++ code in JavaScript and test it. And then as soon as I reach a point where I find something really hard or awkward, I'll just put a function call, because I have this call primitive, right? And I put it to do, and I'm like, later I'll come back to that. And at this point, we have like 3 to-dos left, and they're all kind of hard. So the rest of this talk is going to be like, how do we solve each of these awkward problems in this data-only environment where we don't want to actually need to break CFI? And the first one, which I guess some of you might have guessed already, is locking, right? We need to interact concurrently with these C++ data structures from JavaScript. And the first time I did this, I just like iterated through the lists, and the exploit worked like most of the time. It's like nobody modifies it at the same time. We're all good. That's not really ideal. So yeah, we want to take locks. We want to drop locks. Taking locks, I mean, it's a spin lock, right? What can go wrong? I know user space spin locks are frowned upon, but for our purposes, this will do fine. So this is how you unlock a lock, right? Yeah, kind of. So in this case, and this is what happens maybe 9 out of 10 times, right? Everything is totally fine. I'll add, you can actually do some extra tricks. So if you modify the internals of the mutex, you can make it so that other threads will spin on it for a bit first, and some things like this that you can get it kind of like, your exploit will only stall maybe. This happens. So this is the other case. This is the bad case. JavaScript is holding a lock. C++ code comes to take that lock. The C++ code is like, OK, I better wait. The JavaScript code is like, oh, I'm going to unlock that. And the IO thread is gone, right? Like the IO thread is just going to sleep until the browser process kills us because we're not talking to it anymore. And I went through a sort of denial phase here where I was like, somewhere in the Blink code, I will find a function which will acquire a lock and then call into JavaScript. And then when the JavaScript returns, it will release the lock. Surely somebody has written this in Blink. There is so much code. And after a day of grepping through, I was like, again, you're being dumb. Like, there is just no reason that, like, it would just be so broken that it's like impossible that this would exist. So I found this instead, which is not that. This is part of the web codecs API. And all there is to really say about this is we have this small object. This small object contains a mutex. When we call this function, that mutex is acquired and then immediately released. And this object is actually referenced from the video frame object, which is actually directly exposed to JavaScript. So this is one of the bindings objects. And this object has a pointer to that frame handle object. So by calling this timestamp function, we can get a pointer followed to lock a mutex and then unlock the mutex. So this gives us a primitive basically to lock and unlock immediately a mutex. And that's enough to actually fix our problem. So we're sitting here, the IO thread is stalled. When we unlock the mutex, we can actually see somebody else is waiting for us to release that mutex. And we need to now add another thread, the left gap kind of foreshadowing that. So we add in a worker. And what that worker will do is forcibly unlock the lock, so just set it to unlocked, and then start spinning using that primitive to lock and unlock this mutex. And while it's going, we're just going to race it in the main thread, and we're going to try and flip the bit which says somebody else is waiting on this mutex. And yeah, in this case, we lost. we lost again. But eventually, the main thread will flip this while the worker thread is holding the mutex. And then when the mutex is unlocked, the IO thread wakes back up, and we can continue. Yeah, pretty cool. So, second place. So, we've got locking. We've implemented all of this stuff. But at some point, we have to actually send these messages. And on Linux, there's actually two ways they're sent. One is shared memory. That's easy, but that doesn't work for all messages. So we actually need a pipe write. And writing to a pipe is a syscall. If we look at the actual channel code, there is a fallback path that will get triggered basically if the pipe is full. So you could say, well, like, okay, let's just send lots of messages, the pipe will be full, and then we can quickly, but like, that's going to cause loads of allocations. We're trying to write an exploit, right? We don't want to like DOS the browser process just to send a single message. Like, that's not going to happen. So we need to find a way, basically, to mimic the bold function call at the bottom here, wait for write on IO thread, no lock. And that, initially, I just used a function call here. But if we look at what that function does, is it's just going to post a task onto the IO thread. Now, post task itself is not tremendously complicated. Again, there is some locking, there's some sort of lockless magic and things, but eventually you're just shoving something into a queue. I would note that this is probably the most sketchy part in terms of future mitigations, because we do have to fake a C++ object that contains like a function pointer, right, effectively. So maybe you could imagine some current mitigations that might try to do something to stop this from being easily forgeable. I don't think that any current implementations would make this actually very hard, but if you do, feel free to talk to me about that later. So all we have to do actually is create this fake task and add it to this queue. I did spend 2 days debugging why the exploit didn't work after I did this. Even though these tasks were getting run, the exploit didn't work. The exploit didn't work because the tasks were getting run really late. Tasks were getting run really late because the IO thread wasn't doing anything. So there is a load-bearing cookie set in my framework that just causes the IO thread to do some work so that it picks up these tasks and sends the messages. And that's all you need to do, just to force this message queue to exit so that it actually picks up this task. So we can send messages. And we're left with really one problem left. And this is kind of a tricky one because, again, maybe if you've been thinking, well, maybe that's a bit much to expect to follow. And anyway, we have these traps that we discussed, right? And if we receive a message in JavaScript and it needs to be dispatched to the C++ code, we might have to fire one of these traps. But we already know these traps contain arbitrary function pointers. So, like, this is the code where it would happen, right? So if we'd received a message on a message pipe and we actually need to dispatch that message, and it turns out that that's the next message that message pipe is waiting for, so that message pipe goes from non-readable to readable, then that port status has changed. We need to actually fire that trap, which means we have to call this function pointer. So there are basically 3 cases here. So the first one, we have our exploit code in JavaScript. It's sending some message through this proxy. It's going to another process. If we get a message back, it's going to the JavaScript, so we don't care what the C++ code thinks. It's not a problem. We have our exploit code in JavaScript. It's sending a message to the local C++ code. This is a problem, but we don't care because you're not trying to exploit the local renderer, right? So why would you send this message? Unfortunately, this case we actually do care about. So this is when we're proxying a message from the browser process to the local C++ code, and that would make a message pipe readable. And then we need to actually dispatch this trap. We need to call this function. One way around this would be to literally re-implement the entire renderer in JavaScript inside the renderer, so that you could just dispatch this to your JavaScript implementation of all of these interfaces. I would not recommend trying to do that, but again, if you do it, I would love to see the code. What I actually did was complain to my teammates about how this was impossible. And as often happens when you say something like that, Jan Horn was like, "It's really easy. What are you complaining about? You just need to add more indirection." So indeed, double down, add another renderer. Suddenly, all of these messages that were process local and problematic, now they're not process local, right? Every message we want to deliver locally, we just bounce through another renderer. The problem is solved, and the C++ code just handles it for us. Yeah, and at that point, the end. We have a full, effectively mitigation-safe Mojo JS future-proof implementation of Mojo from JavaScript, and you can go on and write. I mean, I never actually got around to writing the exploit because it took me so long to write the framework that I was like, oh, it's OffensiveCon already. So I guess I'll probably go and do that at some point. But yeah, I do intend to release the code. At least the simple polyfill should be releasable fairly soon. But I'm not making any promises. I would also like to write some blog posts about details, but again, there is so much stuff to do. So, but yeah, any questions?